There's a planet just 4 light years away that could host life, oceans, atmosphere, everything, and yet we have absolutely no way to get there. Not now, not ever, unless we break the laws of physics themselves. This is the terrifying truth about Proxima b. We've always looked up wondering if we're truly alone, and for the first time in human history, we might have found a real candidate for life beyond Earth. Proxima b, a rocky planet orbiting the closest star to our Sun, Proxima Centauri. It's just over 4 light years away. That's practically next door in cosmic terms. And it might have liquid water, a stable atmosphere, maybe even the building blocks of life. It's not just a scientific curiosity. It's a potential second home, a lifeline, a destination for the next chapter of human civilization. But here's the paradox. The closer we look, the more unreachable it becomes. Because getting to Proxima b isn't just hard. It may be one of the greatest unsolved problems in the history of humanity. So the question is no longer, can we go? The real question is, what would it take to even try? Space doesn't just challenge our technology, it breaks our intuition. When we talk about planets next door, our minds picture something close, reachable, but close, in cosmic terms, is an illusion. Let's start small. The Moon. It's 384,000 kilometers away, a place we reached with 1960s technology, wearing suits with less computing power than your digital watch. Then there's Mars, our big red target, hovering at about 54 million kilometers during its closest approach. That's already a massive leap. But Proxima b? Not millions, not billions. It's over 40 trillion kilometers away. That's 4.2 light years. So far, that sunlight takes 4 years to get there. Let's put that into human terms. If Earth were a basketball, the Moon would be a tennis ball about 7 meters away. Mars, nearly a kilometer off. And Proxima b? It'd be another basketball on the other side of the planet. Let that settle in. Now, let's talk speed. The fastest object humanity has ever launched is Voyager 1. It travels at about 17 kilometers per second, or over 60,000 kilometers per hour. At that pace, it covers roughly 540 million kilometers a year. Pretty fast. Until you remember, Proxima b is 40 trillion kilometers away. So how long would it take Voyager to reach it? Over 76,000 years. And that's if Voyager were even heading in that direction. It's not. Let's be honest, 76,000 years isn't a journey. It's a civilization-ending sentence. Humanity wouldn't survive long enough to welcome its own probe back. And here's the most uncomfortable part. That's our best-case scenario with current spacecraft. The truth. We've never sent humans farther than the Moon. Not one human being has traveled more than 400,000 kilometers from Earth. That's not even 1/billionth the distance to Proxima b. So why haven't we gone further? Because we're not held back by ambition. We're held back by physics. The energy needed to move an object, even a small one, through interstellar space is staggering. The vast emptiness isn't just cold and dark, it's resistant. It doesn't want you there. And if you push against it with the same technology we use to launch satellites or space stations, you get nowhere, slowly. Right now, we are prisoners of speed. Even the most advanced rockets we have, like NASA's SLS or SpaceX's Starship, are designed for interplanetary, not interstellar travel. They may get us to Mars in months, but to Proxima b, they wouldn't even make a dent. That's the harsh reality. For all our progress, for all our satellites, telescopes, rovers, we're still crawling on the shores of an infinite ocean. And, standing on that shore, we can see something. A planet. A rocky world orbiting the red dwarf Proxima Centauri sitting in the habitable zone, a place that could, maybe, harbor life. We can see it, we can study it, we can dream about it, but we can't touch it. Not now, not anytime soon, unless something changes. So here's the question we're left with. Why not just go faster? Add more power, build bigger rockets, push the limits. It seems like a simple fix, until you realize what faster really means in the vacuum of space. When we imagine space travel, we think of rockets, towering beasts of fire and thunder, ripping through the sky with unimaginable force. And why wouldn't we? Rockets got us to the moon. They built the ISS. They send probes to Jupiter, Saturn, and beyond. But in the vast scale of interstellar travel, rockets are like trying to cross an ocean using a matchstick and a paper sail. They were never designed for the stars. The problem isn't just speed, it's fuel, and the cruel math behind it. Every kilogram of fuel you carry requires even more fuel to push that fuel. The heavier your spacecraft, the more energy you need, and the more fuel you need to carry that energy. It's called the Tsiolkovsky rocket equation, and it's a brutal limiter. To push a 1-ton spacecraft to just 1% the speed of light, you'd need more fuel than the mass of the entire Earth. Not metaphorically, literally. Think about that. 13 billion tons of fuel to move 1 ton. And that's just 1% the speed of light, not 10, not 50. At that speed, it would still take 400 years to reach Proxima b. So we try to optimize. Use the best chemical fuels we've got. Liquid hydrogen, liquid oxygen, exotic compounds with insane energy density. Still not enough. Even if we built the largest rocket in history, 10 times larger than Saturn V, it wouldn't change the outcome. Chemical propulsion hits a wall, and we've already slammed into it. So why not just keep adding fuel? Because with every drop you add, you need even more fuel to carry it, and the cycle spirals out of control. You end up with a ship that's 99.99999% fuel and still can't get past a tiny fraction of light speed. It's the most expensive treadmill in existence, and it goes nowhere. That's why no one's seriously planning to send a rocket to Proxima b. It's not ambition that's lacking, it's practicality. And let's not forget the human factor. Sending a crewed mission multiplies the problem. You need life support, shielding, food, oxygen, redundancy, and mass. Every extra kilogram, more fuel. Every extra year in flight, more systems, more complexity, more cost. It's a logistical nightmare that collapses under its own weight before it even leaves Earth. Even automated probes face the same wall. Voyager 1, our most successful deep space mission, is still only 0.05% of the way to Proxima b, and it's been traveling for nearly 5 decades. If we want to escape our cosmic neighborhood, chemical rockets must die. That sounds dramatic, but it's the truth. We are reaching the absolute limits of what fire and pressure can do. So if not rockets, then what? Could electricity, plasma, nuclear reactions? Is there any technology, real or theoretical, that can finally break the wall? As it turns out, there is. And some of it is already being tested. If chemical rockets won't get us to Proxima b, what will? The good news is we're already working on alternatives. The bad news: even our best ideas still feel like science fiction, but some of them are real and flying right now. Let's start with one that's already in space. Ion propulsion. It doesn't rely on combustion like traditional rockets. Instead, it uses electric fields to accelerate charged particles, ions, and eject them at high speeds. The thrust it produces is minimal, barely enough to move a sheet of paper, but it's steady, continuous. Over time, that tiny push adds up. NASA's Dawn spacecraft, launched in 2007, used ion propulsion to visit two massive asteroids in the asteroid belt, Vesta and Ceres. It became the first probe to orbit two separate celestial bodies. It was a breakthrough in efficiency, but not in speed. Even with constant thrust, an ion engine would still take over 40,000 years to reach Proxima b. A step forward, yes, but still hundreds of human lifetimes away. So we look for more power. That's where nuclear thermal propulsion comes in. Instead of burning fuel, these engines use a nuclear reactor to heat a gas like hydrogen and blast it out the back for thrust. It's more efficient than chemical rockets and produces more power than ion engines. In theory, it could drastically cut down the time to reach Mars. NASA and DARPA are currently developing a program called Drago to do just that. But here's the problem. Even with that added performance, nuclear thermal engines still fall far short when it comes to interstellar travel. We're talking thousands of years just to reach Proxima b. Better than tens of thousands, but still a crawl across a galactic desert. So what if we went a step further? The Vasimer engine, or Variable Specific Impulse Magnetoplasma rocket, might be that step. It uses magnetic fields to superheat plasma, a state of matter even hotter than the surface of the sun, and directs it for propulsion. It's being developed by a Costa Rican-American physicist and former astronaut, Franklin Chang Diaz. Vasimer promises flexibility and scalability. It could, in theory, reduce a trip to Mars from 18 months to just 39 days. That's revolutionary. But when it comes to interstellar distances, even Vasimer falls short. Proxima b would still be 2,000 years away, even at its peak performance. It's better, but not enough. At this point, our ambitions start to collide with insanity. That's where we find one of the most radical ideas ever proposed in aerospace history, Project Orion. Project Orion wasn't powered by plasma or electricity or chemical fuel. It was powered by nuclear bombs, real ones. The concept, dreamed up in the late 1950s, proposed launching a spacecraft by ejecting nuclear bombs behind it and detonating them in a controlled sequence. The explosions would hit a giant metal plate at the rear of the ship, mounted on shock absorbers to soften the impact. Each blast would push the spacecraft forward, boom by boom. It sounds insane, but it was actually tested in part. Not with nukes, of course, but with conventional explosives to simulate the mechanics. And incredibly, it worked. Here's where it gets interesting. With thermonuclear devices, fusion bombs much more powerful than fission, Orion could theoretically reach 10% the speed of light. That means Proxima b could be reached in 40 to 50 years. Finally, a number that fits within a human lifetime. Barely. But the price? Catastrophic. Project Orion would require detonating hundreds of thousands of nuclear bombs in space. Each one is powerful or more powerful than the bomb dropped on Hiroshima. The spacecraft itself would need to weigh over 400,000 tons, with a massive 100-meter-wide pusher plate. And let's not forget, nuclear detonations in space are banned under international law. The political, environmental, and technical risks are staggering. Still, for the first time, we're talking about a method that actually cracks the wall. The wall that chemical, ion, and plasma engines can't break. A method that might, just might, deliver a mission to Proxima b within a human life. We've looked at ion propulsion, nuclear thermal engines, plasma drives, detonating bombs in space. Each one brings us a step closer, but none of them are truly fast enough. Not yet. Because here's the hard truth. The faster you want to go, the more energy you need. And the more energy you need, the heavier, riskier, and more complex your spacecraft becomes. But what if we didn't carry the fuel at all? What if we let the universe or something far more powerful do the pushing for us? That changes everything. The idea of riding light through space sounds like fantasy. It brings to mind ancient myths of gods carried by sunbeams or chariots racing through the sky. But the truth is, this might be our best shot at reaching another star. Welcome to the world of solar sails, a technology that doesn't rely on fuel, engines, or even explosions. Instead, it uses the pure force of light. Here's how it works. Photons, the particles that make up light, don't have mass, but they do carry momentum. When they hit a surface, they push, ever so slightly. It's a tiny force, almost nothing. But in space, where there's no resistance, no gravity, and nothing to slow you down, that tiny push can build up over time. Imagine a spacecraft equipped with an enormous, ultra-thin reflective sail, like a space parachute. As sunlight strikes it, the sail begins to accelerate, slowly at first, but constantly. Over weeks and months, the ship gathers speed, building momentum in silence, without burning a single drop of fuel. This isn't just theory. The Icaros probe, launched by Japan's space agency in 2010, successfully demonstrated solar sail propulsion. It used sunlight to navigate through space. The concept works, but there's a problem. The farther you get from the sun, the weaker the light becomes. The pressure drops. The acceleration slows. To get a meaningful push, you'd have to start very close to the sun, where solar radiation is strongest. But that introduces a new nightmare: heat. Deploying a sail near the sun means exposing your spacecraft to temperatures of thousands of degrees Celsius. To survive, the sail must be ultralight, ultra-thin, and capable of withstanding heat that would melt most metals. And even if you solve that, the journey would still take 1,000 to 2,000 years to reach Proxima b. So engineers started asking, what if we replace the sun? Instead of waiting for sunlight to push the sail, what if we fire high-powered lasers from Earth or from orbit? Lasers that would blast continuous beams of energy directly at the sail, pushing the craft faster and faster, well beyond what the sun could ever achieve. This is the basis of the laser sail, also known as a photonic sail. Here, we're no longer relying on natural light. We're using directed energy, controlled, focused, powerful. If we had a laser array with, say, 25 gigawatts of power, we could accelerate a small spacecraft to 20% the speed of light. Let that sink in. That's 60,000 kilometers per second. A trip to Proxima b in just 20 years. Now we're talking about something within reach. But of course, it's never that simple. The spacecraft can't be large. To achieve those speeds, it must be incredibly small, just grams or kilograms in mass, with a sail stretching tens of meters wide, a feather riding on a beam of pure light. And those lasers, they'd need to operate non-stop for years. They'd require global coordination, flawless precision, and enormous amounts of energy. A deviation by even a fraction of a degree, and the spacecraft would veer off into the void forever. Still, the idea is so promising, so bold, that it led to one of the most ambitious space initiatives of the 21st century, Project Starshot. But before we go there, let's go even deeper into the mad science. Some theorists have proposed hybrid systems, combining sails with explosive propulsion. One concept, called Project Medusa, replaces the solid metal plate of Project Orion with a sail-like structure. Small nuclear explosions occur in front of the sail, releasing energy, which pushes the sail forward. It's wild, dangerous, maybe even impossible, but it shows how far we're willing to go. In these concepts, the sail isn't just a tool. It becomes a shield, a force amplifier, a way to tame violent energy and turn it into movement. Imagine a future where we send massive light-catching sails through deep space, pulled by beams we fire across the stars, or explosions we've learned to control. Each of these technologies bends the line between science fiction and science fact. But they all share something crucial. They free us from the tyranny of fuel. They remove the need to carry energy with us, and instead, let the environment do the work. Whether it's light, explosions, or plasma, the future of space travel might look nothing like what we imagined. And yet, one project is closer than all the rest. It's not theory. It's not just talk. It's happening right now. And if it works, it could be the first time humanity touches another star system. Imagine a fleet of spacecraft, no larger than a postage stamp, flying silently through interstellar space, each one traveling at 20% of the speed of light, headed straight toward another star. This isn't a sci-fi film pitch. It's real, it's funded, and it's already in development. This is Project Starshot, humanity's most ambitious attempt to reach another star system within our lifetime. Launched by the Breakthrough Initiatives and backed by names like Stephen Hawking and Yuri Milner, Starshot proposes something radical. Don't send one massive ship with fuel, crew, or heavy engines. Send thousands of tiny probes, each one small enough to sit on your fingertip. Each one equipped with a camera, a transmitter, and a light sail. And each one launched from Earth's orbit into the unknown. The plan sounds simple. A mothership would carry these miniature spacecraft, called starships, into low Earth orbit. There, they would be released into space. From Earth, or possibly the Moon, a powerful array of ground-based lasers would lock onto each sail and fire a continuous beam of light, accelerating the probes to speeds never before achieved. 60,000 kilometers per second. That's 20% of the speed of light, fast enough to reach Proxima Centauri in just 20 years. It would be the fastest object ever created by humans, by far. Faster than Voyager, faster than any rocket, faster than any military aircraft or missile or particle ever launched from Earth. Once the probes arrive, they would fly by Proxima b, the most promising exoplanet in the system, collecting data, images, and atmospheric readings. And then they would turn around, figuratively speaking, and transmit that data back to Earth. But here's where the real challenge begins. At such incredible speeds, even a tiny grain of interstellar dust could destroy a probe instantly. The sails must be ultra-thin, yet incredibly strong. The electronics must be compact, energy efficient, and hardened against cosmic radiation. And the communication systems. They must send information across more than 4 light-years of space, using only milliwatts of power. It's like whispering across the ocean and expecting someone to hear you on the other side. To overcome this, Starshot doesn't rely on a single probe. It relies on numbers. If thousands are launched, a few will make it. A few will survive the journey, transmit back what they saw, and change everything we know about our place in the cosmos. This is no longer a dream. The prototypes are being designed, the lasers are being studied, and the technology, though still in early stages, is moving forward. The goal? Launch within the next 2 decades, which means that within your lifetime, you might see the first real photograph of a planet orbiting another star. Not a simulation, not an artist's rendering, a true image sent from the edge of another solar system. That's the power of Starshot. It doesn't promise landing. It doesn't promise communication with aliens. It promises something far more powerful, proof that we can go. It would mark the first time a human-made object escapes the sun's dominion and visits another system entirely. And if it succeeds, it will rewrite the story of our species, because once we know it's possible, even at tiny scale, we'll never stop. We'll build better sails, more powerful lasers, smarter systems, and eventually, bigger missions. First flybys, then orbiters, then landers, then, who knows, maybe colonists, maybe descendants of the people watching this video right now. Starshot won't be easy. It might not even work, but it's more than a project. It's a statement that we refuse to be bound by gravity, by distance, by fear, that we will reach beyond our tiny blue planet and touch the stars. If reaching Proxima b is our greatest challenge, what comes next may be even more unimaginable. We've sent probes to every corner of our solar system, to the Sun, to Jupiter, even beyond the orbit of Neptune. But two destinations remain almost impossible: Pluto and Proxima Centauri. Pluto, a frozen world at the edge of sunlight, and Proxima, a star so distant that even light takes years to arrive. The problem isn't just distance, it's physics itself. Because to reach them, you need to travel faster than anything humanity has ever built, and then somehow stop. That's why, even after decades of progress, both worlds remain out of reach, symbols of how vast the universe truly is and how small we still are within it. For decades, Pluto was the unreachable dream, the cold, silent frontier at the edge of the Sun's dominion. More than 6 billion kilometers away, it lies so far that light itself needs hours to make the trip. In the 20th century, just imagining a mission there felt like planning a voyage to eternity. And yet, humanity tried. In the early 1970s, NASA's engineers discovered a rare celestial opportunity. Between 1976 and 1978, the outer planets, Jupiter, Saturn, Uranus, and Neptune, would align in a way that happens only once every 176 years. With precise timing, a single spacecraft could use their gravity to slingshot across the solar system, saving decades of travel time. It was called the Grand Tour, and it was supposed to include Pluto. The mission design was brilliant. 4 spacecraft visiting every major planet in one continuous journey. But the price? Astronomical. When NASA canceled the Grand Tour due to cost, only 2 smaller probes survived, the ones that became Voyager 1 and 2. At first, Pluto was still on the table. NASA even considered sending Voyager 1 there after Saturn, but a last-minute decision changed everything. Scientists chose to redirect it toward Titan, Saturn's largest moon, a world with a thick atmosphere and potential for life. It was a scientifically sound choice, but it meant Pluto was cut out of the mission forever. From that point on, Pluto became the planet that always slipped away. Throughout the 1980s and 1990s, proposals kept resurfacing, smaller, faster probes that could reach Pluto before its fragile atmosphere froze as it drifted farther from the Sun. But every time budgets collapsed, priorities shifted, and time ran out. It was simply too far, too slow, and too costly. Even solar power was useless out there. Sunlight was just a faint whisper. Any mission to Pluto needed radioisotope generators, nuclear power, and even then, energy would be limited. But a handful of scientists refused to give up. Among them was Dr. Alan Stern, a planetary scientist who led the charge for decades. He argued that Pluto wasn't just a frozen dot, it was a world, one that could hold secrets about the solar system's origins. His persistence finally paid off in 2001 when NASA approved New Horizons, a small nuclear-powered spacecraft built with a single goal: reach Pluto before it was too late. Launched on January 19, 2006, New Horizons became one of the fastest human-made objects ever created, accelerating to over 49,000 kilometers per hour. Even at that speed, it still took 9.5 years to get there. When it finally arrived on July 14, 2015, It didn't stop. It couldn't. It raced past Pluto in a single flyby, capturing the first and only close-up images of that distant world. For a few days, humanity saw what once seemed impossible: glaciers of nitrogen ice, blue hazes, and a heart-shaped plane carved into the frost. But even in triumph, the truth remained. Getting to Pluto was never the hardest part. Stopping there was. When New Horizons flew past Pluto in 2015, it didn't slow down. It couldn't. And that single fact explains why reaching Pluto and beyond is so deceptively difficult. It's not just about getting there, it's about stopping once you do. In space, speed is survival. To escape Earth's gravity, a probe must accelerate to at least 11 kilometers per second. To reach the outer planets, it needs even more, tens of thousands of kilometers per hour. But the farther it goes, the faster it must move to complete the journey before decades turn into centuries. And every kilometer per second gained on the way out must somehow be undone if the spacecraft ever hopes to slow down. That's the paradox. The faster you travel, the harder it becomes to stop. When New Horizons left Earth, it was designed for one purpose: a flyby. It didn't carry the fuel or propulsion system necessary to break into orbit around Pluto. Doing so would have required a rocket stage almost as massive as the spacecraft itself, plus decades of extra travel time. At 6 billion kilometers from the sun, sunlight is so weak that solar panels would barely power a light bulb. And chemical fuel, the kind used to reach orbit around nearby planets, becomes useless when you need to decelerate from 49,000 kilometers per hour in near-zero gravity. To enter orbit around Pluto, the probe would have needed an engine capable of firing continuously for months and an enormous supply of propellant. Even a tiny burn at that distance requires staggering energy. Every gram of mass adds years to the mission. So instead of trying to stop, New Horizons simply flew through, capturing as much data as it could in the few hours it had while racing by at incredible speed. And that's the same challenge that makes Proxima Centauri even more impossible. If reaching Pluto took 9 years at record-breaking speeds, imagine traveling to the nearest star, more than 4.24 light-years away, or 40 trillion kilometers. At the velocity of Voyager 1, humanity's fastest interstellar probe, the trip would take 76,000 years. And even if we could somehow accelerate to a fraction of the speed of light, we'd face the same dilemma. How do you stop when you arrive? A spacecraft traveling at 10,000 kilometers per second, just 3% the speed of light, carries kinetic energy equivalent to thousands of nuclear bombs. Slowing that down requires propulsion systems far beyond our current technology. Nuclear engines, ion thrusters, even advanced plasma drives like VASIMR could cut the travel time to Proxima from millennia to centuries, but not enough for a human lifetime. And every improvement in speed multiplies the braking problem. You can't simply turn around in interstellar space and fire your engines. You'd need as much energy to stop as you did to start, and most of that fuel would have to be carried from Earth. In other words, the faster you want to go, the heavier your ship becomes, and the harder it is to move at all. That's why missions like Voyager, Pioneer, and New Horizons never slow down. They're designed to drift forever, carrying humanity's curiosity out into the dark. They can escape the sun's gravity, but not their own momentum. It's humbling to realize that in the grand scale of the cosmos, we've only taken the smallest of steps. We've learned to throw our machines into the void, but not yet how to bring them gently to rest on another star. For now, Pluto marks the edge of what we can reach, and Proxima Centauri remains the edge of what we can only dream about. Humanity's journey to the stars has always been limited by one word: propulsion. Every leap forward in exploration from the Moon to Pluto has been defined by how fast we can accelerate and how efficiently we can slow down. But to reach beyond the solar system, we need to reinvent motion itself. Today, the spacecraft we launch still depend on chemical propulsion, the same basic principle used since the 1960s. Powerful, yes, but incredibly inefficient for deep space. To reach even 1% of the speed of light using chemical fuel, a probe would require a tank with more mass than Earth itself. It's absurd. And that's why scientists began to dream differently. One of those dreams is ion propulsion, engines that expel charged particles at tremendous velocity. They're slow to start, but in the vacuum of space, they can burn for months or even years, gradually building speed. Missions like Dawn have proven their reliability inside the solar system, but even these futuristic thrusters would take tens of thousands of years to reach Proxima Centauri. Then came VASIMR, a plasma engine developed by former astronaut Franklin Chang Diaz. Using magnetic fields to accelerate ionized gas, it promises journeys to Mars in just over a month. In theory, it could cut interplanetary travel times by a factor of 10, but even if perfected, a VASIMR ship to Proxima Centauri would still need over 2,000 years to get there. That's when engineers turn to the stars themselves for help, to the light that shines from them. Solar sails work not by burning fuel, but by catching photons. Each tiny impact from sunlight pushes the sail forward, slowly but steadily. Enormous, ultralight, and fragile, they're like cosmic parachutes drifting on beams of light. They could, in theory, reach another star in 1 or 2 millennia. Still far too long for human ambition, but revolutionary nonetheless. And then came a radical twist on the idea: laser sails. Instead of waiting for the sun, we could use Earth-based laser arrays to push the sail at unimaginable speeds. This concept became Breakthrough Starshot, a plan to send swarms of microprobes, each the size of a coin, to Alpha Centauri at 20% of the speed of light. The journey, only 20 to 30 years. It's bold, dangerous, and maybe the first step toward interstellar travel within our lifetime. But there's a catch. Even at those incredible speeds, the probes wouldn't stop. They'd flash past Proxima in seconds, capturing everything they can before being lost to eternity. The truth remains, we've mastered the art of leaving home, but not yet the science of arriving somewhere else. For centuries, humanity has stared at the night sky and seen distance as a challenge, something to be conquered. From the first telescopes of Galileo to the robotic eyes that now wander through the darkness, our species has always asked the same question: how far can we go? But now, standing at the edge of what we've achieved, the answer is humbling. We can go far, but not far enough. Pluto and Proxima Centauri stand as two cosmic mirrors, one at the frozen edge of our sun's light, the other orbiting a distant star. And between them lies the same barrier, the cruel mathematics of distance and energy. We reach Pluto with brilliance and stubbornness. New Horizons showed us a world of mountains made of ice and plains shaped like a heart, a symbol of endurance frozen in nitrogen and methane. But even as those breathtaking images arrived, the probe was already racing away, silent and unstoppable, never to return. It was a victory that came with a price, proof that visiting the edge of our solar system is still closer to a miracle than a routine. And Proxima Centauri, it mocks us from just beyond reach, a mere 4.24 light-years, our closest neighbor, and yet impossibly far. At our fastest speed, a probe would take longer to get there than all of human history itself. Even if we could build ships capable of crossing that gulf, we'd still face the same problem that haunted New Horizons: speed without control, motion without return. Every proposed solution, fusion drives, nuclear pulses, antimatter engines, solar sails, faces the same cosmic truth. Space is vast beyond comprehension. Each meter per second gained requires energy on a scale that defies practicality. And even if we solved propulsion, communication would break down, navigation would falter, and the time delay between now and then would turn into decades. The deeper you go, the more alone you become. That's why missions like Breakthrough Starshot matter so much. Tiny ships, lighter than a sheet of paper, accelerated by laser light. A fleet of 1,000 eyes sent into the void. They might not slow down, they might not survive the journey, but they represent something more important than success. They represent intention, the human need to push forward even when the destination is unreachable, because that's what exploration has always been, an act of faith. When we sent Voyager, we knew it would never come back. When we launched New Horizons, we knew it would never stop. And if we ever send a mission to Proxima, we'll know it won't return to tell us what it found. But that has never stopped us. Each of these journeys isn't just about science, it's about who we are. To venture outward, to reach for what's impossible, is to defy the boundaries written into our biology. We are creatures of gravity, bound to one small world, yet our minds refuse to stay here. We build machines to become our extensions, to see, to touch, to wander where we cannot go. And someday, maybe centuries from now, one of those machines will slow down. It will enter orbit around another star, and it will send back an image, not of home, but of another home. A pale blue dot circling a faint red sun where the story of humanity begins again. Until then, Pluto reminds us how far we've come, and Proxima reminds us how far we still have to go. Between them lies the truth of our age. We are explorers trapped in the slowest century of discovery, standing at the dawn of a cosmic era we can almost touch. So we keep pushing. Each launch, each failed mission, each grain of data from a dying probe, it all carries the same message into the stars. We are here, we are trying, and even if we can't yet cross the interstellar gulf, every light we chase brings us one step closer to who we're meant to become. Because in the end, the road to Pluto showed us that far is only a word. And the road to Proxima will decide whether impossible is one too. There's something haunting about the way our greatest missions end. Voyager, still whispering from the darkness after almost half a century. New Horizons, drifting beyond Pluto, chasing sunlight it will never feel again. And one day, perhaps, the sails of Starshot will do the same. Tiny messengers of humanity, gliding silently between the stars. Each of these probes is more than metal. They're echoes of who we are, dreamers, engineers, explorers. Every signal they send is a heartbeat from Earth, a reminder that curiosity is our oldest instinct. Because the farther we travel, the more we realize space is not just a destination, it's a mirror that shows us what we're capable of becoming. When New Horizons revealed Pluto's frozen heart, it wasn't just science, it was symbolism. At the edge of the solar system, a heart still beats. And beyond that, Proxima Centauri waits, our nearest neighbor and our greatest temptation, 4 light-years away. A distance that defines what impossible truly means. Yet we keep trying. We design faster engines, lighter sails, bolder missions, not because we expect success soon, but because hope itself demands motion. And maybe that's the secret of our species. We're fragile, but relentless, limited, but unafraid of infinity. Someday, our descendants will look back and see these early attempts, Voyager, Pioneer, New Horizons, as the first flickers of a cosmic dawn. They'll say, that's when humanity began to expand its horizon, because exploration was never about leaving home. It's about redefining it. So we keep going, past the frozen plains of Pluto, past the fading light of our sun, and into the unknown between stars, not because it's easy, not even because it's logical, but because wonder demands it. And in that pursuit, in that endless reaching, we discover the one thing rarer than any planet or star: ourselves. If you could choose just one destination, would you rather visit Pluto's frozen heart or Proxima Centauri's unknown world first? Tell me your choice and your reason in the comments below. Like this video if it made you wonder how far we'll truly go. Subscribe to Stellar Path and join me as we travel beyond the edge of the known universe.